Okay, hello and good evening everyone to another of our webinar series, which is part of the Timber Development UK Southside Hereford University Design Challenge, which has been undertaken in partnership with ourselves at NMITE, the New Model Institute for Technology and Engineering, Edinburgh Napier University, where I also continue to have a role. Because we're establishing the NMITE CAT in partnership with the ENU, and our other partner on the TDChallenge22 Design Challenge, which is Passivhaus Trust. We have a whole series of sponsors, which you can see along the bottom of the slide there. A headline sponsor is actually Transforming Timber, which is a Construction Scotland Innovation Centre-led project, with which ENU are a partner to, as well as Ecosystems, a property technology startup. And we're also engaging with the University of Edinburgh on that project with regards to fire performances that happened. And Luke Bisbee spoke earlier on in the seminar series, and we'll hear more about fire this evening through our invited speakers. Transforming Timber itself is an Innovate UK funded project to accelerate the use of UK timber in construction practices with an emphasis on mass timber. Anyway, we have a series of other partners or sponsors to the project also, including Torero, PFC, TDCA, AECB, and the underlying sort of competency framework work was also sponsored by the UFI Volktech Trust. We have Trimble, Wood for Good, Akoya, and Rothoblas, and indeed recently we had a webinar in itself where a number of the sponsors spoke at. So the challenge itself, Southside Hereford, which you'll likely be aware of having tuned in before, but essentially we're looking at university students to create multidisciplinary teams to respond to a design brief to create a sort of community centre, which is a collaborative approach between NMITE, Belmont Wanderers and Growing Local, to create a new building of 800 metres squared with a budget of 1.6 million. This is a live project, so indeed the work that's undertaken through this design competition will ultimately inform the delivery of this project. It's looking at the community centre, which should enhance the sort of local biodiversity and help to regenerate the lives of the people within the community. And of course, the building should respond in many respects to the future ways of delivering projects given the climate crisis. So it should have a minimum impact to the site and the planet, and ideally, well, it will be predominantly delivered using timber. And of course, we wanted to also have a high fabric performance and therefore respond in a manner which is fitting with the sort of passive house approach. So this is purely a schematic. Please don't use this in many respects in terms of how you want to respond to the challenge, but it's just to give you an understanding of the sort of site, the building, and how it's to respond within the current landscape, and create a centre point for the respective organisations, and out with the project itself will be a community garden and football pitches, etc. So beyond the building, it's got other attributes to it, but fundamentally this design competition or design challenge is about the delivery of the building using timber technologies with regards to the brief and the budget and the stakeholder requirements. So as I said previously, we've had a number of other webinars in this series, and you can go and revisit those, and indeed this one will be posted on the YouTube channel, so loads of good content there. There's full information on the challenge in itself via the TRADA website, and there'll be future activities also. As much as we're coming to the end of the webinar series, we're going to have a selection of follow-on sort of workshops and tutorials, etc., to help inform how you respond to the design challenge. So keep an eye out for those also in Eventbrite. Tonight is all about the subject of fire, a very relevant subject in the current sort of climate as such, you know, off the back of the Grenfell, etc., and what that's meant in terms of regulation change and government response and how that's affected the delivery of timber buildings. There's been knock-on effects as a result of that, limiting, you know, having height restrictions in terms of timber buildings, particularly around those for residential use, etc. And we all know that timber is a combustible material, but ultimately we want to explore how you can design and deliver timber buildings safely. So that's the premise, really, to provide a broader understanding of this subject matter this evening through expert speakers. So we're very privileged to have a really good selection of speakers with us this evening. We have Andrea White. Andrea is an independent fire engineer supporting designers and developers. She's proud to be an incorporated engineer with the IFE, a chartered building engineer with CABE, and an IFE registered fire assessor. She is proud to be an incorporated engineer. Andrea is chair of the Women in Fire Engineering Networking Group, as well as a lead interviewer and panel member for the IFE's Fire Risk Register. With a background in fire safety enforcement, consultancy, and the insurance industry, Andrea has a particular interest in timber construction. She was telling us before this she was trained to be a forester, and is also ensuring appropriate fire safety measures for those with invisible disabilities. We'll have Jose Torero Cullen, head of UCL Department of Civil Engineering, Geomatic and Environmental Engineering. He works in many aspects of fire safety engineering, remediation and sanitation. He has developed novel methodologies for the safe design of complex buildings such as tall buildings, historic architectures or timber structures. He has studied major environmental problems such as oil spills or large underground coal fires, where he has developed unique approaches towards impact mitigation. And Jose has conducted extensive research in engineering education that has resulted in the development of successful education programs in fire safety engineering worldwide. And then we have Martin McLaggan, who's a lecturer in low carbon design at the University of Sheffield. The main theme of his research is safe, sustainable structures. His work seeks to quantify risk and use this to safely enable the use of innovative materials and technologies in the built environment to reduce carbon emissions. He specialises in the fire performance of low carbon materials, design of modern buildings, and facade and cladding fires. So I don't think we could ask very much for a better selection of speakers this evening. So with that, I'll hand over to Andrea and stop sharing myself and let her start presenting. But please do put any questions that you have within the chat and we'll pick them up as we go through the webinar. So with that, I'll stop sharing and hand over to yourself, Andrea.
Thank you, Robert. Right, let's see if I can do this. How is that? Is that working?
All good.
Yeah, great. Okay. Let's just sort this out. Okay, so good evening, everybody, and delighted to be here on International Women's Day. So thank you for inviting me. I've been asked to speak today on the role of a fire engineer for roughly the next 25 minutes. So I planned this presentation, and when I was thinking about doing that, I decided to structure it by addressing these 6 question words: how, where, why, who, what, and when. But it's probably helpful at this point to say that my talk relates to new build construction. Fire engineers also get involved with existing buildings, but given the design challenge that this webinar is talking about, I'm just going to cover new build here. So I'll begin with who, because I haven't yet introduced myself, although I appreciate that Robert has kindly just done that. So I'm Andrea White. I'm a fire engineer and I've got my own consultancy company. I've worked in fire safety for just over 20 years, and I began my career initially in building management and health and safety, where I worked for a number of years. Then I joined a fire and rescue service to work in fire safety enforcement, and I also trained to be a retained firefighter. When I left the fire service, I then decided to spend a decade working in consultancy and then 5 years working for an insurer. So from this description, you can see that I've got quite a broad practical background of both managing buildings and assessing the fire risks in buildings. What I'm trying to show you is that fire engineers can come from a really wide range of backgrounds. They might come from laboratory fire testing work, they might come from operational firefighting or structural engineering, or maybe mechanical engineering. I mean, there's lots of different ways to come into fire engineering. So each fire engineer will tend to bring a different set of knowledge and experience with them. But third-party accreditation means that that individual gets assessed by a group of peers and they have their competence verified. So in my case, I've done that, and I'm very proud to be an incorporated engineer at the moment through the Institution of Fire Engineers. And that's shown on my post-nominals with the part that says IEng FI FireE. I'm very proud as well to be a fellow of the IFE. I've also been assessed by CABE to be a chartered building engineer. And then that logo on the right shows that I'm a third-party accredited fire risk assessor. So moving on from why, let's look let's look at why we might have fire engineering as a discipline. So I'm going to take you back a bit. If we start by looking more broadly at building safety, we have legislation under the Building Act to secure the health, safety, welfare and convenience of people in and about buildings. And then to fulfil that duty, we have the building regulations. Now, those are scheduled under 17 separate headings, and they're scheduled from Part A to Part S at the moment. And these cover all manner of different aspects of construction, structure, ventilation, drainage, accessibility, glazing, security, and most recently, Part S, charging of electric vehicles. So for each different part, you can see here we have some guidance on how we meet that regulation in the form of an approved document. And here I'm showing you approved documents A, F and L1A. Now, regulation which covers fire safety is Regulation B. And Regulation B has 5 requirements that I'll cover in a minute. So the image on the left is the front cover of approved document B. I've just said we have guidance in the form of approved documents for each regulation. So this is the approved document for Regulation B. But I've also included on the right a picture of a horse behind a stable door. And that's because in this country, we have a policy of stable door safety legislation. And that means that we tend to invoke safety legislation after a significant incident has happened. So most of our regulations and legislation can be traced back to a substantial loss of life that has occurred. And we then put in regulations or legislation to put in measures going forward to try and prevent that happening again. We can see that in terms of additional legislation that is being brought in right now as a result of the Grenfell Tower tragedy. The other why question that came to my mind is, why have a fire engineer on a construction project? And that's a valid question. Historically, really up until the last few years, architects would tend to design the fire safety aspects of most buildings, and certainly most simple buildings. And that left fire engineers to work on more complex projects, maybe buildings such as transport hubs, very tall buildings, or buildings where the design wanted to challenge the way we've met the requirements and create maybe what we called an engineered solution. But for several reasons, as a result of the Grenfell Tower fire, fire engineers are now being used on more construction projects and are more involved during the whole build process. That's a little bit about why we have fire engineers. Now let's go on to what fire engineers actually do. So what do fire engineers consider? Well, there's 3 potential objectives that the client might ask us to consider. And I've tried to depict these in the images on the right of this slide. The first at the top, which we have to consider as part of the building regulations, is life safety. So people are generally quite surprised when they learn that building regulations only address life safety aspects, but Part B of the building regulations only looks at keeping people safe from fire. We've got two other objectives that we could consider, but they're optional, and they are property protection, which I've depicted here with the house, and business continuity, which is the image on the bottom there. So the client will initially decide whether they only want us to meet life safety objectives, ensuring people in and around the building are safe from fire, or whether they also want to protect the building itself, and or whether they also want to protect the business that operates within that building. So meeting additional objectives in addition to life safety will mean adding increasing levels of safety, which means increasing levels of fire protection measures. Now, Regulation B itself, the fire safety requirements within that are split into 5 aspects, and we term those B1 to B5. They're called functional requirements. They tell us what we need to do, but functional requirements don't tell us how we need to do that, and we'll have a look at that in a minute. So let's look at the 5 fire-related requirements for life safety that we need to meet. So first of all, B1 then. This covers means of warning and escape, and you will notice how short this requirement is. It's the first column there, and it's only a couple of lines long. The B1 requirement is basically we have to design and construct the building with appropriate provisions for the early warning of fire and appropriate means of escape in case of fire. So what does that actually mean? So in looking at means of escape, fire engineers will look at quite a number of different things. And I'll just give you an example of some of the things we would look at in relation to doors as an example. We would look at how many people are likely to be in the building and how large the footprint of the building is. We would look at how far people would need to travel to get to relative safety. We would look at how many doors we would need, whether a single door is enough or whether we need multiple doors. We would look at how wide the doors need to be to accommodate everybody to be able to leave in a reasonable time. We'll look at which ways the doors need to open, whether they can open inwards because there's not too many people, or whether they need to open outwards so we aren't prevented from opening the door because of the crush of people behind us. And the way that the doors open is an example of that stable door legislation that I mentioned earlier. We'll also look at mechanisms to open the doors on an escape route. So you can see here that this door on the left has a push bar, and that allows quick and easy opening. In terms of means of warning, a fire engineer will look at whether a fire alarm is required, and if so, whether we're looking at a domestic grade of fire alarm or a commercial grade of fire alarm. Here in the image, I've put a commercial grade, and for some types of premises, we would require heat and smoke detectors for life safety, but for other types of premises, we might just require manual cool points like this red break glass that I've put in here. So the standard we need to provide in any particular building is determined by that word appropriate, and this means it will be a lower level of fire safety measures if you're building somewhere where people are awake and can relatively quickly and easily leave the building by themselves, maybe a small shop or perhaps the community centre that we're designing in this challenge. But we would look for a higher level of fire safety measures in something like a care home or a hotel, perhaps where people stay overnight and sleep, or where they might not be able to leave independently, or in a large building where there's lots of people, maybe like an airport or a large auditorium. So moving on to B2, that relates to internal linings of a building, and that's the walls, the ceilings, and sometimes the floor linings within the building. And this is because if we have a fire, we don't want the flames to spread along those walls or across that ceiling. And again, this is an example of stable door legislation. So something like this is what we're trying to guard against, although these drapes won't have been part of the building design. If there was a fire in this room and these ceiling fabrics weren't suitably fire retardant, we would expect the fire to spread fairly rapidly across this ceiling. We would traditionally expect the walls and ceilings to have a plaster or a plasterboard finish internally. Now, if you're building in timber, this would generally mean encapsulating the timber in plasterboard. And aesthetically, many architects want to expose that timber. So a fire engineer might consider how we could justify leaving that timber exposed. And there's a lot of research going on at the moment around exposed CLT in relation to fire spread. So moving on to the third fire safety requirement, B3, that relates to the structure of the building and fire spreading internally, thereby affecting the structure. So if you are building in structural timber, which we know is combustible, this is going to be a regulation that needs some careful consideration. But remember our objectives. If we are building only for life safety, then we need to ensure that everybody is able to evacuate the building with a suitable safety margin before the stability of the structure is compromised. But if we're looking to achieve property protection and ensure that structure remains standing throughout any fire, then we probably need a higher level of protection and greater fire safety measures. So this was the Moorfield Hotel in Shetland, and it had a fire 2 years ago, which resulted in complete loss of the building, as you can see here. But there were no fatalities and no casualties. So in terms of life safety, we met the B3 requirement because it maintained its stability for a reasonable period of time in terms of life safety. So we're back to the question about what are the client's objectives? Are they only life safety, or are they looking to protect the property and to protect business continuity? Obviously, this business could no longer trade, and property protection didn't occur, as a result of this fire. So moving on to regulation B4, that's about external fire spread. So here we're looking to ensure that flames don't spread over the external walls of the building, or if one building has a fire, that fire doesn't spread to neighbouring buildings. So for this reason, we consider roof coverings to make sure that flaming debris doesn't get dispelled in a fire and land on neighbouring roofs and set fire to them. And obviously this requirement is very much related to the Grenfell Tower fire. And I would suggest that if you want to understand this aspect better, I can't think of a better way of learning more about that than to watch some of the expert witness evidence from the fire engineers at the Grenfell Tower inquiry. Those are all posted on YouTube. So lastly, we have requirement B5, and that relates to access and facilities for the fire service. So the requirement is for reasonable facilities to assist firefighters in the protection of life. And there again, there's that reference to life rather than to property or business continuity. And there's also a requirement for reasonable access for fire appliances, and that means ensuring that fire engines and other firefighting vehicles can get there via the roads and bridges, make sure that they're wide enough and sufficiently weight bearing to take those vehicles. So for B5, fire engineers will check that the access roads are wide enough to get a fire engine near to the building to enable the firefighters to fight the fire. And for tall buildings or those with deep basements, we would look at providing dry or wet risers. And those are effectively a fixed vertical pipe which extends up through the building, and firefighters can plug their hoses in at the base, at the inlet, which you can see here on the right, and then connect more hoses on a floor nearer the fire, and then they don't have to drag hoses up lots and lots of floors to get water there for firefighting. Now, for B5, I've included this slide because it's a really good example of an instance where B5 issues have needed to be overcome. This is a fantastic hotel complex in Devon, which I had the pleasure to go and see. It's right by the sea, as you can see. And you can see on the right here, you can see the access road. It's incredibly narrow, very winding, and up a steep gradient or down a steep gradient. The hotel then decided they wanted to build some beach huts, and you can see those just on the left-hand side with the pointy roofs. I think there's 6 of them in two levels there. Now, in order to satisfy the B5 requirements, those beach huts ended up being sprinklered. It was an alternative solution to meeting the normal distances for access. And this is a really good example of the role that a fire engineer can play on a project. How do we go about designing into buildings measures that meet these 5 requirements, B1 to B5? Well, there are 3 ways that fire engineers can use different types of design codes. So the first way is the simplest way, and that uses the approved documents, which I mentioned earlier. There's an approved document for all of the 17 parts of the building regulations, Part A through to Part S, and it's a guidance document for each part, which offers a prescriptive solution to how you could meet those requirements. I suppose basically the approved document gives you a blueprint for each type of premises. And if you correctly follow that approved document, then you are deemed to have satisfied those building regulations. Now, approved document B for fire safety runs to just over 200 pages. And I've just given you a couple of pages as an example to see how that document goes about that. Moving on to the second of the 3 different ways we can meet B1 to B5, that's slightly more complicated. It's a risk-based solution. So for the type of building that you're designing for this challenge, we would use British standard BS 9999, whereas for blocks of flats, for a risk-based solution, we would use a different standard, which is BS 9991. So a risk-based methodology of meeting B1 to B5 allocates a risk profile to the building based on the occupancy and also based on the anticipated fire loading within the building. So we look at what sort of materials are likely to be present, because that will affect how quickly a fire will grow. So why do we look at fire loading? Well, let me give you an example. I'll give you sort of 2 extremes, if you like. You could have a stonemason's workshop where everything is stone and therefore everything is non-combustible. If you contrast that with the other end of the scale, you could have a bed shop where everything is combustible and you've got beds and mattresses, you know, lots and lots of beds and mattresses stored in there. So the risk-based approach considers more variables and allows more flexibility in terms of trade-offs between various measures than ADB does, than approved document B does. So for example, if you've got some taller ceilings or a higher level of detection in your building than is required, you can potentially extend travel distances. There's some mitigations, there's some trade-offs there. Now this document runs to over 400 pages, and I've shown you here just a couple of pages as an example. And then finally, there's a third way. The design codes that I've just mentioned, approved document B and BS 9999, they're generally adequate for most buildings. But this third way is a much more flexible solution, and it looks to apply fire safety engineering principles. So this approach uses a British standard called BS 7974, and we would only tend to use this British standard where you couldn't use the other design codes, perhaps because we've got a large or a complex building or an innovative design. Those using this methodology are now looking to make assessments and professional judgments rather than following a more prescriptive code. So we need to make sure that the people who are doing that are suitably qualified and experienced in fire safety engineering. So fire engineers will set out how the functional requirements in B1 to B5 are going to be met in a fire strategy document for the building. And generally these are fairly substantial reports, perhaps running to 40 or 100 pages. BS 9999, which I mentioned earlier, it gives quite a nice, concise definition of a fire strategy as a set of fire safety objectives and the measures to be taken to meet those objectives. So the fire strategy sets out whether we are looking to meet just life safety requirements or whether we're considering property protection and business continuity. And generally it contains some plans like the one I've shown here, just to depict those fire safety measures that it's looking to include in the building. So the penultimate question is, when is a fire engineer involved in a construction project? And for this, I've shown the REBA plan of works with stages running from stage 0 concept to stage 7 in use. And traditionally, if fire engineers were involved at all, they would only tend to be involved in REBA stages 3 and 4, which I've circled in red, and they would be asked to write a design fire strategy. Now, only being involved in those middle stages isn't really ideal in two ways, for two reasons. Firstly, at REBA stage 3 or 4, much of the design has already been agreed, and that means the fire engineers don't have much opportunity to influence that design. And that often means that compromises have to be made to accommodate fire safety aspects. And the second point is that if you don't involve a fire engineer in the later REBA stages, that design fire strategy doesn't get updated with any amendments that are inevitable during construction. So as a result of the Grenfell Tower tragedy, these sort of difficulties, issues are starting to be addressed, and we're seeing fire engineers now beginning to be engaged throughout the whole project at all REBA stages. So I've tried to show in these yellow box flowcharts here. So we should now see greater fire engineer involvement during construction and ensure that design fire strategies become as-built fire strategies when we provide them to the client at handover. And finally, where do fire engineers work? Well, we do a lot of our work at our desk. I'm here in my office now. We check plans, we make assessments, and we write reports such as fire strategies. But we also go out on site. So we'll go to check that building works are being done how we've asked for them to be completed. We'll go to site to discuss any changes that need to be made to fire safety measures or questions that the construction professionals might have about fire safety measures. And I've just included some photographs of me doing an external wall assessment of a block of flats. I'm looking at photographs taken of wall makeups and deciding where to make an intrusive inspection on a building. So that concludes my presentation on the role of a fire engineer. I want to wish you all good luck with your design project, and I'm happy to try and answer any questions on the role of a fire engineer at the end of the 3 presentations. Thanks very much.
Excellent. Thanks so much, Andrea. That certainly laid out the roles and responsibilities of a fire engineer, and I'm sure gave those training a better understanding of what it's all about, and indeed where your role starts to come to the fore within that, the REBA sort of plan of works, etc. So that was really useful, and of course very useful indeed when considering the nature of a timber building. So it's good to have that in mind before going about the design process and the different ways that you can approach it. So to follow up on that, I see now that Professor Jose Torero has joined us from UCL. I gave your intro at the start, Jose, so without further ado, if you were able to share your screen and then take us through your presentation on explicit design of fire safe timber structures. So with that, I'll hand over to you. Thank you very much.
Can you hear me?
Yeah, perfect.
Excellent. Okay, so I think, and Andrea has set up the stage perfectly well to understand how our building regulations work and what are the different tools that that we have to be able to understand, to be able to design and buildings. And she's also talked a little bit about some of the limitations of the current approach towards the role of fire safety engineering and its involvement in projects, and the obvious result of potential problems. So I am going to talk a little bit more about timber in itself, and more from a physical perspective and the challenges that that brings. And I think one of the fundamental problems when it comes to the design of timber buildings is that we have to address timber buildings in a very fundamental way. Normally, when you produce documents like BS 9999, or you produce the guidance for approved document B, this information is based on understanding and applications that are currently used, for the purpose of the safe design of buildings. And even if you get to the more sophisticated fire engineering documents, they're still based on fundamental, I would say, practices that are currently being used. Now, the more you get into the complicated documents and the more you get away from the guidance of approved document B, you are going to find out that the more you need to understand the physics, and you need to understand the behavior of the different materials as it pertains to the design that you're going to do. Now, you still will always have to respect the functional requirements of the approved document of the building regulations. So you still have to produce a fire safety strategy that delivers the word adequate when it comes to B1, B2, B3, B4, and B5. And but adequate is no longer defined by the guidance, because the guidance is restricted, to some examples of very common practice. It is not defined by BS 9999, because BS 9999 is based on existing practice. And when, as I say, when you get to the more complex documents, really all you have is a compendium of the physics, and the designer is the one who has to deliver the analysis. Now, when it comes to innovation, and when it comes to timber buildings as such, as an innovative product in construction, very rapidly we realize that this is a problem that is unique in nature, for which there is very little precedent, and for which there is no guidance or any British standard or approved document that truly applies. And this is where we create a little bit of a problem, because many times, we enter into the space, into the confusing space of trying to fit this guidance or these documents into a problem for which the guidance and the documents were not designed. And I think this is where we need to be extremely careful, because right now there's an enormous confusion on how to design timber buildings, and it is basically defined by the fact that there is very little competency in the practice on the safe design of timber buildings when it comes to fire, and this almost obsessive approach, to try to use existing documentation, to try to resolve a problem that cannot be resolved by those means. So I'll give you a few examples just as a brief introduction, so that you understand the fundamental physics that is relevant and why that fundamental physics cannot be found in a document like BS 9999. So if you look at a building like the one in this picture, so this is King's 25. It's the tallest fully exposed office timber building in the world. And this particular building demonstrated not only a new process of design that enabled a fully exposed timber building, to be built, but also determined a new process of approval. So this was done in Australia, and before King's 25, many of the authorities would never accept a building like that. But as part of the design and build of this office building, a new process of approval was defined, and that process of approval effectively has been used now in multiple other buildings in Australia. So where are we right now? So around the world, there's a lot of code changes, and this code changes. The most recent one is in the United States, where, for example, the ICC board is International Code Council. Sorry, I don't know what's happening with, let me put all this in. So the International Code Council basically opened the door to allow buildings of significant height to be designed out of timber. And in exchange, they introduced more sprinklers, and they introduced more fire resistance requirements. Now, this is a typical approach that we follow. So we try to fit the existing approach to regulation into a problem that it is completely different. So keep in your mind the two words, the more extensive provision of sprinklers and the more significant fire resistance. These are the two things that were used as a concession to allow timber buildings to be taller. In the rest of the world, the confusion around timber buildings and cladding issues like Grenfell has resulted mostly in the opposite. Instead of relaxing the rules, what we're doing is banning the use of timber in multiple typologies of structures. So in principle, you can see where the confusion is, in the sense that half of the world is banning timber and the other half of the world is relaxing the use of timber. And in all of these cases, there's very little scope to really understand the material specific challenges that we actually need to address. So in the meantime, we keep seeing significant fires around the world. Just recently, there was a major mass timber fire in the United States. But here you have a picture of Notre Dame and the mass timber roof that covered the church. And you wonder, we have an architectural jewel such as Notre Dame, how on earth this could possibly happen? And this could only happen because of a complete misunderstanding of how to provide the appropriate fire safety to a building like that. This should have never happened. So in reality, we know that timber can potentially be an excellent construction material, and buildings like King's 25 shows that that is the case. But at the same time, we do recognize that timber burns. And in some cases, when timber burns, it can create massive disasters. And therefore, the question is, how do we actually design buildings using timber in a way such that we deliver something safe? Now, to be able to understand how we design timber buildings to deliver something safe, we really need to understand what is the problem that we're trying to solve. If we understand what is the problem that we're trying to solve, then we can start thinking of ways by which we prevent this. So this example, as I say, of King's 25 gives you a sense of how far you can go if you do things right. You can design a building that is 10 floors in height. You can basically use timber all over the place. In this case, it's glulam as a primary structure, CLT floors, fully exposed timber, and basically the tallest timber building in Australia, and actually still in the world. So the first question that we need to ask ourselves is, our building regulations are there to protect people. So they're protecting the occupants and they're protecting the firefighters. Now, is designing a timber building a problem for the occupants and the firefighters? So that's the first question that we need to ask ourselves. And that basically brings us to what is a conventional fire. So the picture that you see there is basically a non-combustible room where you actually have furnishings, and those furnishings are burning. Now, these furnishings that are burning are going to deliver a conventional fire. And the question is, if I have a timber structure, is that conventional fire going to change? And is there any change that could potentially happen actually going to affect the potential safety of occupants and firefighters? That is the question I need to answer. So I need to be able to answer that if I change the fabric of the building and I turn the building into timber, am I going to negatively affect the safety of the occupants and the firefighters? So at the end, fire growth is unaffected by the timber structure, and therefore life safety of the occupants is actually not affected. Now, why is that the case? Because if you think about it, timber starts degrading at about between 350 and 400 degrees Celsius. So because it starts degrading at 350 to 400 degrees Celsius, it is not going to ignite until it gets to those temperatures. Now, if you have a room where the room has temperatures of 350 to 400 degrees because of a fire, that room is going to look like the picture that you have in there. So the conditions will already be untenable. So people could not be in a room with such high temperatures at the same time as the timber is igniting. So timber structures actually ignite way after everybody has to be outside the building. So they have to be away from the area of the fire before the timber structure can possibly ignite. So while we can argue that the timber will eventually ignite, and in that case, it will affect the safety of firefighters, the timber, in principle, will only ignite long after people have left the room. So in principle, it shouldn't affect at all the life safety of people. So when people think, for example, that they're going to improve life safety by adding sprinklers, they're just simply not understanding the problem. Sprinklers are going to activate and they're going to do something to the fire. But the reality is that all people will have evacuated before the sprinkler activate and way before the timber has ignited. So in that sense, the sprinklers are by no means a mechanism to make timber safer. They're just basically something that makes all fires probably reduced in probabilities, but it is not a specific tool that I'm going to be using to try to make timber safe. So what I'm looking for, if I want to protect the firefighters, and if I want to, for example, enable the evacuation of people in a tall building where it takes a very long time to evacuate, it is that I need the timber to actually confine the fire and do not allow the fire to spread. But I do not also want to have my structure being affected, because the collapse of the structure or the failure of the structure can actually have a problem on the life safety of the firefighters. So the only way that I can achieve that, and this is the second part of the problem, is that if once the furnishings or the fuel inside the compartment is consumed, that the structural timber will self-extinguish. This is the only way I can guarantee structural integrity. So what do I mean by that? If you have a chimney and you have logs and those logs are burning, the reason why they're burning is because you have set them up in a certain way that heat from one burning log is supporting the burning of another log. And because that feedback of heat is enabling the continuous burning, you can have your chimney burning for a very long period of time. The moment you take one log out of the chimney, that log will extinguish immediately. That's what we call the process of self-extinction. So the real problem that we need to address, if we want to guarantee structural integrity and we want to guarantee the safety of the firefighters is that the structural timber self-extinguishes. And that's what I need to prove. That is not in approved document B guidance. That is not in BS 9999. That is nowhere to be found in any of the standard documents because this is unusual. This is innovation. Now, nevertheless, to be able to guarantee that the firefighters can operate safely, which is part of B5, which is the functional requirements that are inherent to the fire safety strategy, you need to be able to guarantee that the timber self-extinguishes. Because otherwise the timber will continue to burn, you will get structural failure, and when you get structural failure, then the firefighters are compromised. Now, so at the end, if you think about it, timber is not a problem of life safety for the occupants because the occupants would have evacuated the building appropriately. It is a structural problem that in a very tall building, it can affect the occupants because the occupants will take a long time to evacuate. So if you get structural failure, you will have a problem. But mostly it is a problem for firefighting because if the timber continues to burn, then the structure will fail and it might fail while the firefighters are trying to fight that fire within the building. Much later in the process, generally much after the evacuation process. So why does timber self-extinguish? Because it produces a thick char layer. And the thick char layer doesn't let the heat get to the timber, which is at the bottom, and therefore it doesn't allow the timber to degrade, the process that we call pyrolysis. And because it stops degrading, then it stops producing fuel, and then the flames die. Now, fire resistance is what I explained at the beginning was the concession to allow for tall timber buildings. Now, fire resistance is a test that is done with a furnace. And that furnace corresponds to this curve that you see, the one that continues infinite in time. Fires are the other curves, and fires heat up and die. Now, my expectation is that the timber should self-extinguish after the fire dies. So then what's the point of doing fire resistance when the fire of the furnishings never dies? If what I'm trying to understand is if the fire can self-extinguish, then why would I subject it to a fire that never dies? If the fire never dies, the timber will inevitably burn, and it will continue to burn while the furnace is on. The moment I turn the furnace off, then the timber might self-extinguish. But if it never turns off, then it will never self-extinguish, and I'm never testing what I want to know. So fire resistance as a concept, as is embedded in the guidance, as is embedded in BS 9999, is actually meaningless when you really want to understand how to design a timber building. And this is what happens. If this element is being tested in the furnace, it will continue to burn while the furnace is on. So basically, you can have a failure criteria when you have standard testing conditions, but that is fire resistance. And fire resistance is a concept that unfortunately is not valid unless the timber reaches self-extinction. Okay, self-extinction is what we're looking for, and a fire resistance test will never give me that. So here you can see an example of a test. What I have the furnace on, this heater heating up the timber, you can see the timber is burning. In other words, is producing fuel. You can see this 8 to 10 number is the production of fuel. As soon as I turn the furnace off, the char doesn't allow the burning to continue, and very rapidly the fire self-extinguishes. Now here you have a test that actually shows that at a real scale, where you have a few exposed timber faces, and you set this whole thing on fire by burning this wooden crib, which represents the furnishings. So the wooden crib is going to burn, producing a fire that produces this type of temperatures, like all the way up to 1,000 degrees. Okay, so there's a period where it's going to be very hot, but then eventually the fire is going to die. Now, would the timber continue to burn? So if you look at what happens is basically the fire of the crib starts, it starts getting more intense. Eventually, it starts getting really hot, and by the time it gets to 350, 400 degrees, you can see there's flames, all over the place, and the timber in the ceiling has already ignited. Okay, if you have people inside the room at that point, those people will be dead. So the moment of ignition of the timber is much, much later than anything related to life safety. The fire continues to grow, it gets very intense, and then eventually, as the crib is fully consumed and there's no more furnishings, then the fire slowly starts decaying until all by itself, it self-extinguishes. Okay, this is the way that you want your building to behave, and this is the performance criteria that matters. Okay, this is what you really need to assess. Now, the problem is unfortunately a bit more complicated because these products are actually a combination of timber and glue. And sometimes the glue fails, and that produces what we call delamination. In other words, pieces of wood start falling off. And if pieces of wood start falling off, then they start feeding the fire, and then it never reaches self-extinction. So structurally, you have to prevent delamination, and that is another performance criteria that you need to address. Here you have an example of delamination. You can see the planks coming out as you heat up the timber. Okay, so these pieces of timber will come off and they will fall off and feed the fire. Now, the problem with glue is that glue fails at very low temperatures, much, much, much lower than timber. So at the end, it's the weakest link. So protecting the glue line becomes an objective of design and something that you should be trying to do when you do a design for a timber building. So another way of trying to prevent the timber from burning and achieving self-extinction is by encapsulating. In other words, covering everything with gypsum wallboard. Now, the problem with that is that first, it has to be done right. And two, if you put too many layers, timber loses completely its environmental credentials because gypsum wallboard has a lot of embodied carbon. So, and if you do it wrong, then even if you protect it with plasterboard, the plasterboard might either fall off or the timber might burn behind that. Because in reality, if you want self-extinction, the plasterboard should protect the timber in such a way that it doesn't ignite. So, in essence, this is a complicated problem. It is not within the realm of our existing guidance or our existing standard documentation. It's a unique innovation that requires you to understand the physics of the problem. Now, I've gone really, really fast, and I didn't really expect you to understand the details of what I'm saying, but nevertheless, it gives you a sense that we need to be looking where it matters. We cannot use standard approaches like fire resistance and sprinklers when in reality the problem is about self-extinction and delamination. So it is about focusing your design on the things that actually matter. And there's a lot of literature that you can consult to try to understand better these concepts, but focus on what matters, which is guaranteeing self-extinction and guaranteeing that your timber doesn't delaminate. Thank you very much.
Brilliant. Thanks very much, Jose. That followed perfectly from Andrea, and I think we'll follow very nicely into Martin as well. That was absolutely fascinating. I didn't think it was too quick at all. I actually thought it was just nicely on point, and thoroughly enjoyed you taking us through the nuances of timber buildings and how the current regs don't really fully respond to them, which then hopefully lines up Martin quite well. Martin, can I ask you to take over the screen as such, and we look forward to your presentation. So thank you.
Hello. Yes, my name is Martin McLaggan. I'm lecturer in low carbon design at the University of Sheffield, which I think means I might have the coolest job title in the university, and maybe across different universities as well. Yes, you're going to see a lot of similar messages to Jose's presentation. Hopefully it means if he went too fast, it means that you can see the same messages re-emphasized and in a slightly different way. So the title of the presentation was How Timber Products Perform in Fire. And then the kind of subtitle was Strategy for How to Use These Products. So you can probably already start to see that there's going to be the same messages kind of popping up. So I wanted to start with traditional buildings and how these were designed to really emphasize how we originally went about this and why so much has now changed. We typically had structures which were non-combustible, and our strategy was to maintain compartmentation, and it was to ensure they would last for the duration of a fire. So once the furnishings would extinguish, then your compartment, your structure would still survive. In terms of cladding and the exterior of the building, again, these were specified to be non-combustible. There'd be an adequate spandrel or distance between the floors to be defined to ensure there wouldn't be fire spread between floors. So that would be how we maintain vertical compartmentation. And then the linings, maybe more recently, we had the Euroclasses system around the year kind of 2000. So this did include combustible materials, or they could be combustible. You basically expose them to a range of tests, and then you evaluate their performance to look at the growth phase of the fire. So just on those a bit more briefly, Jose's furnace looked a little bit newer than the one that I have. I think this one's been in use for a few decades. This is a fire resistance furnace. So while our structures were typically non-combustible to begin with, what we have is now combustible structures. Jose's already made the point that timber will continue to burn as long as you expose it to some sort of exposure. And we also have the case that timber will burn, and we have certain difficulties with these tests because the timber will contribute fuel load, yet the furnace doesn't actually respond to that. So even the way that we use these tests is a little bit off. Reaction to fire, I've missed out the 11925, the spread of flame test. So essentially, when you have linings in a building, if you want to go the prescriptive route, then you go through a series of tests. It's the 13501 framework if you want to go through all the numbers. It's mainly based around the single burning item test, which is this one here. You have two walls of your material, you have a fire exposure, and based on how much heat is released for a very limited duration fire, then you see how much energy is released and how it performs according to fairly arbitrary limits. Almost immediately after this was released, they had problems with the fact that while it was intended to be used on solid materials, so a single layer plastic, or maybe more realistically plasterboard or wallpaper, carpets, kind of things like this, and solid wooden products, it immediately became the case that we started to see products and composites and much more complicated systems being tested. And we already started to see serious problems with this test and how it can actually evaluate those types of materials. And it goes back to the point of looking at what we actually intend and what we actually want to know from these tests. But we start to find when we look at products in this test that it doesn't really give us the information that we need. The two tests on the left are the kind of very basic ones, which are just about evaluating whether or not a material is combustible, essentially. It doesn't really tell us anything more than that. If I go on, and then we have I've included facade in most of this presentation, so I haven't really focused solely on the structure. I've gone more into kind of timber buildings and the idea of kind of wooden products and walls and what have you. So I've included facades here. They're slightly different because they're much more modern compared to, for example, the furnace testing. And they've not really been, we obviously see a lot of work going into them right now. You normally have a huge wall up to around 8 meters high. You have some sort of fuel source at the bottom. And then you have temperature measurements at arbitrary points. And then you kind of check whether this passes or fails. But it doesn't really tell you much about what's going on. It doesn't really feed into your strategy. It doesn't really tell you much about whether you'll have adequate performance or not. And clearly this is something already under extensive review. Obviously, we already know this affects timber buildings because it's led to the ban in certain scenarios. So we already know this is something we kind of need to look at. So how does our building environment look like now? So these are some tests we did in 2017. It was on, I think, 9 or 8 different kind of green buildings. One of them, for example, is a green wall, and it was tested in 3 different configurations of wet, dried, and then I think somewhere in between. You can also see on the right-hand side a kind of a wooden facade, fairly complicated in how it's built up. I've also included, this is hemp, but you can also imagine wood fiber insulation. So we have insulation materials being designed or constructed using renewable materials, and then also timber compartments. This is probably the least interesting photo I could possibly have used, so I do apologize, but I hope you get the point. So we can hopefully see from this slide just how different that was from the original slide and the idea of these non-combustible structures, these linings with limited growth, and spandrels and walls, which are also constructed from non-combustible materials. Oh, there we go. So I just wanted to pick up on one of the details from actually the previous week, which is maybe a little bit cheeky. We have, on the left-hand side, we have the outside of the building, right-hand side is the inside. Going from left to right, we start with the outer cladding layer. We then have a cavity in the battens to attach this. We have some sort of membrane to protect the building from moisture. We have wood fiber insulation in the middle. And then on the right-hand side, we have cross-laminated timber as the structure. And I wanted to kind of talk about the fact that some of the risks and some of the things that we want to look at or consider don't really fit into what was originally intended. So as Jose has already mentioned, we kind of have to think about differently and think about what the risks actually are, because those won't necessarily be covered by the guidance, which never saw any of these materials being used and never expected any of this to happen. And as we continue to go forward, we'll see more and more challenges or more and more kind of different and novel ways of construction. And a lot of how we need to approach this is trying to identify those risks rather than waiting to be told what those risks are. So on the next slides, I'm just briefly going to go through those. Upward flame spread is clearly one which is rather well known on the outside of a building. So the design intent is that a fire should not spread from one floor to another. Wooden products have the benefit that they are charring materials, so they have a tendency to inhibit growth, but at the same time that needs to actually be shown, that needs to be demonstrated. And part of the problem we have now is that they're banned without really any route to show that. But as we go forward, it should be the case that you have to prove that it won't spread flames up your building. And if you can do that, then you can say, okay, I passed that clause. There's the possibility of cavity fire spread, maybe not so much here with the battens, but this is one of the concealed modes of fire spread. So this is where the flames grow inside the cavity. There'll be anywhere where you have thin gaps, which with the super complex systems that we have can exist all across buildings. The more complex the system you have, the more likely it is to have these kind of risks start to creep in. Insulation materials tend to have a very low thermal inertia. Their goal is to trap heat in the building. And the effect is that in fire, if you have them exposed, they ignite extremely rapidly. They're also low density, so a lot of the time they don't release that much energy, but the rate at which these materials ignite is quite incredible at times. In this slide here, I have the insulation is hidden behind, so you wouldn't actually have that. There is also the smoldering risk. I should maybe just note here, I'm really kind of covering all the possible things that could come up. Jose's already kind of nailed the ones that you actually care about and the ones that you actually want to look at. But I wanted to cover all the possible things which need to be evaluated or things you say, okay, I don't think this would be important. The cross-laminated timber, so if we have a combustible structure, then one, we have the contribution to a compartment fire. That'll be particularly important if you have multiple surfaces, as we'll kind of see later on. and the potential for delamination. So this is loss of the outer char layer or the failure of a glue line, where you lose the outer layer or several layers of the cross-laminated timber, and it can keep propagating through. Kind of as we've mentioned in both the previous presentations, actually, despite all these kind of different risks, it's really about looking at what you actually want to achieve and then thinking about how you achieve that. So one is whether you want to look at life safety or property protection. So as Jose kind of mentioned, if you have these timber materials in your building, it doesn't necessarily affect the growth, in which case people are able to escape the building, especially if it's a low-rise building. You get a high-rise building, then you have this really, you need to look at the performance of the structure, because then the time it takes for people to evacuate starts to overlap with the time of structural failure. And then you seriously start to kind of threaten lives of firefighters and potentially occupants in the building. I'm also looking at what the type of the building is. So housing and commercial would be very different. Hotels, care homes, and what the building's used for will change what the resulting fire strategy will be. Very briefly, I've just given generally some of the layers of protection which we have available. We saw in the last presentation already, speaking about sprinklers. The very first thing that we have is detection and alarm. So normally smoke detectors are extremely sensitive, and if the fire is not in a concealed space, then we can actually detect them rather quickly and set the alarm, which hopefully means that people can escape from the building as soon as possible. One of our most critical ones, especially in the UK, is compartmentation. So this is also touching on encapsulation. So this is ensuring that the fire does not spread from one room to another and one floor to another. A lot of our strategy in the UK and elsewhere is really heavily based on this and ensuring that this is maintained. If compartmentation is not maintained, then we start to encounter really serious issues. And we have firefighting, particularly to aid evacuation and structural integrity to ensure that the building will stand up, especially when there's firefighters or occupants still in the building. So encapsulation, these are a series of tests just recently published. This is the idea of using plasterboard. As Jose mentioned, the more and more plasterboard you use, then the higher your embodied carbon, and then it starts to go against the goals. But we can use this plasterboard to prevent the delamination and ensure that we achieve self-extinction, which is really our ultimate goal in ensuring that we protect lives. Jose already had the full graph and all the pictures. I think this is the first time that I've tried to remove most technical aspects from my presentation, but you already saw the full series. But in these series of photos, I'm just showing that if you have sufficient encapsulation, then you can still have some exposed timber, but it ultimately achieves self-extinction, and in that way you guarantee the life safety of people in the building. So I do have some large compartments just to add some videos and make it maybe slightly more interesting at the end. So this is a compartment which has it's vermiculite walls, it's essentially mineral walls. We have wood cribs for our fuel source, and then we have a non-combustible ceiling. And we have the fire traveling along. So in large compartments, we already have different behavior from small compartments, which is another thing we need to start consider. This is something that we really don't quite understand yet. I'm also wondering if I'm actually going to be able to show the other video. Well, it starts anyway. So in the second video, we have a cross-laminated timber ceiling. In reality, this actually spreads more slowly, but both videos are sped up, so it's a little more difficult to see. We have this spreading along the fuel, and at some point we will eventually have ignition of the ceiling, and then we rapidly spread to the rest of the compartment. Actually, in these tests, the spread in the CLT compartment is slower because the thermal inertia is higher. So the insulative properties of the compartment are extremely important. So sometimes it's not just as simple as combustible versus non-combustible. Even when you have non-combustible materials, the properties of those materials is extremely important in describing the fire growth. See if I can go on. Some of the strategies kind of already mentioned. So use of fire retardants. Use of fire retardants is not an automatic solution. It doesn't make it safe and then you're finished. It is a mitigation strategy that we add to try to reduce the severity of the fire and hope that this helps. Using the thicker outer lamella is something that was mentioned in the previous presentation. So if we want to maintain compartmentation, if we want to ensure self-extinction, then one strategy that we have is when you have the cross-laminated timber, if you have a thicker outside lamella, then you can prevent or increase the time it takes for delamination, hopefully prevent delamination. And that way you can achieve self-extinction, and then you can again ensure life safety of the occupants. And then there's just basically a repetition of the last slide. And that is the end of my presentation. So thank you very much for listening.
Great, Martin. Thank you so much for following on with another great presentation. I feel as if we had a lot of really good content this evening, and I think as a result of which we have quite a few questions in the chat. I just need to bring up the chat because I had them up and it's disappeared. Where's it gone? Oh, here we are. So I'll just circle back to the start of the chat. Okay, the first question was, I think, from the first presentation, the hotel that was seen that was burnt down in its entirety there. Andrea, I think that was in your presentation, wasn't it? Was that a SIP spill, or do you know what the fabric of that hotel was?
Yeah, so it was modular construction, that one.
It was modular construction. Was that a timber-based modular construction, or was it, do you know, or?
Do you know what? I don't know the answer to that. I know it was modular. I wouldn't be able to say for certainty with that.
That's okay. Yeah, no problem. Yeah, I'm sure we could look into it. It was a question from Milad and Cheva, who I know quite well. Next one was from Ocean Higgins. Is there currently a BS spec recommended for dry risers, diameter and safe working pressure? I don't know if anybody can pick up on that one.
I'm happy to do that one.
Sure.
So 9990 is the British standard for risers. And then they're asking some questions about diameters and safe working pressures. So diameter wise, you'd have a two-way inlet breaching of 100 mil each, 100 mil pipe. And then a dry mains would have an operating pressure of 12 bars. And I had to actually look up in the British standard the wet main, but it says systems should be designed such that maximum system pressures serving a fire main outlet for wet risers do not exceed 20 bar. So there we go.
Thanks very much for looking that up. How have the fire response strategy changed post Grenfell, specifically in relation to shelter in place and vertical circulation geometric requirements and pressurization and ventilation requirements?
Shall I go for that one, or?
Yeah, if you don't mind, yeah.
So this is a really interesting one, and good question. So this is referring to what we have in this country, which is stay put, defend in place, shelter in place, which is an evacuation strategy we have in blocks of flats, and that is the traditional norm in blocks of flats. We would only deviate and do simultaneous evacuation in blocks of flats for specific, probably compartmentation reasons. I was quite interested, actually, if we relate this to timber. Professor Torero was talking about everyone being outside the building long after the timber structure ignites, and that structural safety is an issue for firefighters. But my question would be, what about where we've got stay put? You know, at that point, is it still a question of only affecting the firefighters? And I'm not sure that's actually the case. you know, I'm a great believer in timber. You know, my first degree is in timber. I'm a big fan of timber, and I understand we need to save the planet for our children and our grandchildren. But, you know, the whole stay put thing plus combustible structures for me sits uncomfortably. Does that make sense?
Oh yeah, and I completely agree with you. I mean, I think that if you are going to use timber, then you have to seriously reconsider the idea of stay put.
Right.
You know, stay put is a policy that is very much a UK approach towards evacuation. And yes, I completely agree with you. I mean, I think the two things are, I mean, you can potentially contain the fire, you know, within a unit by designing things correctly and reach self-extinction before the unit is breached, you know, but you will have to put provisions that are extremely robust and they're extremely well verified. And this is where you consider if actually retaining a stay put strategy is actually that, you know, is such a restriction that why not just change completely the approach and have a proper evacuation strategy, you know, with appropriate, you know, means to deal with, you know, with you know, inclusivity and so forth, and not necessarily, you know, rely on such a simple approach like stay put. So yeah, I mean, I think this is a way of looking at the problem. You have to look at it outside the box completely.
That's great. There was a further question from Ocean here, directed at yourself, Jose, probably building on that, in terms of how do we best manage fuel loading? Are there databases where the fuel load of a piece of furniture equipment is published and maintained by the manufacturer?
Well, I mean, I think that main sort of fuel load is one of those things that that there will always be a range, and there will always be very bad practice, and there will always be very good practice, and obviously we have restrictions in regards to furniture and on the sort of type of behavior that we will accept and that it is consistent with our building regulations. But the fuel load is always an issue of significant uncertainty, and if you want to design appropriately, you have to make sure that you are designing something that is robust for a wide range of fuel loads.
Okay, and then the next question, I think you was it, the question is how does one take this information to building control in a practical and pragmatic manner? So I think that's very much based upon what you're presenting, but indeed what is kind of what you were saying also about when you have to rethink very much the strategies if we're going to start, you know, doing more buildings in timber, right?
Yeah, and it requires a very extensive dialogue from the beginning. No? So, I mean, I think this is a process of education where effectively you're learning and delivering a solution that is robust and acceptable. But in many ways, because it's innovation, you cannot expect that those who are there to enforce the building regulations are going to be fully familiar with what you're doing. So you have to basically carry them through the process and help them understand, you know, in a very transparent way, you know, what is the process that you are you know, generating, and that is a very difficult process. It's not an easy one.
Yeah. Martin, I don't know if you wanted to come in on that at all. I mean, you've probably got some thoughts also with respect to these types of questions, given what you presented also.
Yeah, I mean, probably most of my answers are pretty similar. I think Jose's answered these questions at least a few hundred times before, so I think he gives rather more concise answers than I do in these.
Cool. I think, Andrea, this is the question from yourself, but that was the question that you asked, right? That was did you want to build upon that at all? This was around the radiative feedback between the exposed walls, such as at internal corners. Will this not prevent self-extinction? Understanding that this was in the findings at the RISE tests in Sweden.
Yeah, I mean, the corners are the most vulnerable part of the process, and yes, there is an issue with the corners, but it doesn't mean it's not going to happen. It does happen eventually, and you just have to basically design for it.
Yeah. There's a question here. Could some intermediate spaces be recommended in the design to prevent the fire from spreading between spaces? Can a fire propagation model be created over the 3D model during the design phase?
Martin, I'm going to have to run, so I'll let you answer that question.
No, yeah. Really
It's fine.
Yeah. Of course, we've only got a few minutes, but really appreciate all your time, Jose. That was very insightful, a really good presentation. It was a pleasure to have you this evening, so thank you very much.
Apologies.
No problem at all. Thank you.
Could you briefly repeat the question? Was it for upward or lateral, or neither?
Yeah. So the question, I think, was specifically on probably relating to the design challenge in itself, and the thinking around the use of intermediate spaces. So could some intermediate spaces be recommended in the design to prevent the fire from spreading between spaces? And can a fire propagation model be created over the 3D model during the design phase?
So I think on the first question, yes, I think it's a viable strategy. It's a viable idea. It's kind of the whole idea of compartmentation is to keep it in one area, and then if you keep a kind of second zone, you ensure there's not combustibles in that area. I mean, sometimes that's what corridors are achieving in our buildings. We normally specify that they don't have any combustibles, so the floor shouldn't be, or the floor should be very, very limited combustibility. The wall shouldn't propagate flames, and that should be a sort of safe space in itself. You could extend that concept slightly further. I think those are exactly some of the kind of ideas that you'd want to look at. Can you incorporate it as part of a 3D model at the design stage? So yeah, certainly some of these things, if you know how to do fire dynamics and you know how to use these tools, you could certainly look at them from an initial stage. I think also Andrea kind of hinted this. If you bring in fire safety engineers very early on in the design stage, they can actually really help, and they can start to shape the building in useful ways and change the geometry and say, hey, this area is a problem, or another area is this not really going to be a problem, and you can start to change how the building's going to look. It is possible to do kind of very simple kind of rough orders of magnitude to do kind of models. They give you an idea of what's going on. Sometimes 3D models are quite dangerous because they're nowhere near as accurate as we think they are. So, the idea that you run the model and you get the answers is not the case. But if you go on with a specific question, you can get the answer. And I think one question is that you could say at the design stage, I want to roughly know what's going on. Does it appear that these, zones could be useful, or do they appear to be useless? And then you use that as useful information into your design.
That's brilliant. Because I think Tabitha was just building upon that, but given the nature of this building, it's sort of 1 to 1.5 stories. It's be timber, but it wouldn't be occupied at night. But it will have sort of mixed use, children, other people, etc. So there's probably things to think about in there in terms of the fire strategy also, right? Perfect. I think we've ran out of time, but obviously I actually think this is one of the evenings we've had the most questions and dialogue. So it's obviously a subject matter that people are trying to understand, I think, right? And as a result, it's bringing out all these different questions. So I think we've kind of ran out of time. I think what we'll do is we'll maybe stop recording, and if others want to join Tabitha, then they can do so. And if our speakers want to leave us and go and get their dinner or whatever, we'll let them go, but they're more than welcome to hang on and have conversations with the participant, but they may not have time for that, okay? But with that, well, thank you very much. And it's just to note that, yeah, we have a scheduled event for Thursday, but that's not a webinar, right? That's a Trimble sort of software release and workshop, and then the next of the sort of webinar series in itself will be on the 15th of March, when we will look at quality in the built environment. So we'd build very much on what the topic was this evening, and encourage people to register in for that. But with that, we'll thank you very, both a huge deal for your presentations, and let you go on with your evening. But you're most welcome to stay.